Hello and welcome to a talk on the LibreSoc Power ISA 180nm ASIC. Thank you very much to Ganesan for this opportunity and to IIT Roorkee for the opportunity to present. So, most obvious question is you don't just start an SoC and make a new ASIC just because you want to. You have to have a really good reason, and the reasons are that we wanted to create a replacement for the ASICs that are currently available due to the incredible security issues that are coming out. You will maybe be familiar with the Intel Management Engine, which is a spying backdoor coprocessor built into every single Intel processor since 2009. Apple actually started their own processor because they were using Intel x86 and found more QA issues in Intel x86 processors than Intel found in its own x86 processors. We also have Spectre, Meltdown, and the latest, my favorite one is the master firmware key has been leaked, which allows anybody to reprogram an Intel processor's instruction set to do anything you like, and that's extremely serious thing. But also, there's no transparency. You can't audit commodity hardware, and from a business perspective, this is extremely serious. Companies have been delisted from the Nasdaq Stock Exchange. Supermicro was delisted from the Nasdaq Stock Exchange because they weren't able to prove the provenance of the hardware. And if they had the full, not just the source code of the firmware, but the GDS2 files open for public inspection, they would have been able to challenge the delisting. Likewise, Huawei can't challenge their exclusion from certain markets because they're using ARM third-party products. So you have this, not only this, but you have this endless proprietary driver system where you have a fabulous semiconductor company that sets up with proprietary drivers, because those proprietary drivers come with the hard macros developed by the company, and it's all under NDA, and they just throw it at the thing, and it's simpler, cheaper, easier for a fabulous semiconductor company with no expertise in that particular block, video processing or 3D or whatever it is. They're an assembly factory of the HDL, and if they were to try to do this, it would affect their product development cost if they were to do it thing. But you end up with extremely opaque driver bugs. A classic one was the Samsung S36410, where the released Android 3D driver, you had to call two OpenGL functions in exactly the right order, and if you failed to do so didn't know about this, it segfaulted it, and there's no way that this could be fixed. Your end user application would segfault. There's no way of fixing that. So the alternative is illustrated by this extremely good Intel and Valve Steam collaboration, in which they reported it was the most productive business meeting ever. No NDAs were signed. Both of them were using Libre licensed source code. Intel's 3D accelerated drivers are open source. Valve Steam's engine is open source, and they just met up and organized things amongst themselves. So ultimately then it's a strategic business objective to develop entirely Libre hardware, firmware and drivers so that customers for whom transparency is critically important can inspect everything. Why do we choose OpenPower? Because it's a good ecosystem is essential for doing development of an HDL of any processor. There's 30 years of development behind OpenPower since 1994. You need a Linux kernel, you need U-boot, you need compilers, you need operating systems, you need libraries for libmath, libc6, and you need reference implementations. There's an extremely supportive foundation of members. You also need to be able to submit ISA augmentations for proper peer review, and that process is being set up as we speak. It's been ongoing for a long time, and it's just coming to fruition. There must be no NDAs. Full transparency must be acceptable because our team is funded under the NLNet's Privacy and Enhanced Trust Program. And it turns out that one of the conditions of the transference of the instruction set responsibility from IBM to the Open Power Foundation was that the RFC's request for change to the instruction set be allowed by people who are not necessarily members of the Open Power Foundation. They won't be able to vote on it and its acceptance, and they won't be able to see the process of evaluation, but they will be able to submit, and that was critically important for us. So yes, Open Power is established for decades. It's an excellent foundation. Microwatt we've been used as a reference, and everyone that we've been talking to has been approachable and extremely friendly. It's fantastic. So right, 2 years ago now, we started out, and we had to make a very important strategic decision to choose an HDL. We spent almost 3 months very carefully evaluating all of the options. Chisel 3 was the latest kid on the block, and so we took a look at that. It was unreadable. We also looked at MyHDL, which is a Python-based HDL. We looked at Verilog, VHDL, MeGen, NMeGen, and many others. So we absolutely loved the object-oriented capabilities of Chisel 3. It's just a shame about its being below 20th on the TOBE index. The TOBE is a public score of how used, how many software engineers across the world use a particular programming language, and it's extremely useful. It's a judge of how many people will have the ability in that language, whether they've been trained, whether they're used to it, etc., whether they're used to the ecosystem. Now, the other thing about Chisel 3 is because it is used primarily in academia, academics are not necessarily trained in software engineering techniques. So if you have a look at the average Chisel 3 source code, there's no code comments at all. The only one that I've seen which has code comments is by a software engineer, which is Anton Blanchard with Chiselwatt. MyHDL is also in Python, but it limits itself to a subset of Python because it is literally using the Python syntax as if it was Verilog, and consequently you can't do object-oriented techniques because Verilog doesn't have object-oriented thing. Also, the community is no way as large as that is for NMeGen, so we eliminated it from inquiries on that basis. MeGen the precursor to NumEgen, is really inconvenient. Um, it was an experiment that was successful in its own right. However, you can very easily create not just unsynthesizable Verilog. It creates Verilog where it doesn't check any of the errors for you, and you're working at a level of abstraction, and you can't even catch the errors until the ASIC synthesis level, which could be 48 hours down the chain, and you have a 4 or 5 hour runtime on producing the GDS2 files, and it fails out. So that's just no. Verilog is very much 1980s and 1990s. It reminds me of BASIC and Fortran. We consider it to be machine code, assembler. You don't write you don't create computer programs in assembler unless you want to do them to be heavily optimized. So Verilog is out. VHDL is great. It has records, unlike Verilog. You have to have the proprietary version system Verilog in order to be able to pass records around as parameters to your modules, whereas VHDL you can do that. But VHDL still has no object-oriented capability, and you can't. It's probably Turing complete. No. Ultimately, we chose NumEgen because of a large community and because Python is third on the TOB index. It's been reported recently that between 1, 2, and 3, there's only something like 0.6% in it. So we should see Python becoming number 1 on the TOB index fairly shortly, because it's still climbing. So why do we use to pick? Ultimately picked it because we can use Python to build an abstract syntax tree in memory. So you call a function which returns an abstract syntax tree fragment. There is a signal class which will create a signal, which then it hands that over to Yosys to create what's called ilang or RTLIL files. After which, if you want to, you can create Verilog from it. So Yosys itself doesn't do anything. It's like a thin wrapper on top of the capability of Yosys, but it's an extremely good one with deterministic synthesizable behavior. Yes. Signals are declared with their reset pattern. There is no more forgetting the if reset block and if at always and all that nonsense. It's automatically and inherently created for you by the very fact that you declared the signal at all. We can deploy Python object-oriented programming techniques. We can create classes and functions and inherit from them and pass in parameters which change and augment what HDL is created. And we did an entire IEEE 754 floating point 16, 32, 64 library, and you could very easily create an 80-bit or a 128-bit by passing in four parameters: the exponent and the mantissa size, and that's it. And we created basically a toolkit for creating IEEE 754 pipelines and finite state machines, and have, as a result, all of the common functions and capabilities, such as the normalization and denormalization, which would normally done explicitly and inline things. We created object-oriented abstractions for those, and then use those as building blocks in the floating point HDL. We can also do Python for loops to read, for example, CSV files, and then generate a hierarchical nested suite of HDL switch case statements based on the contents of the CSV files. And this is how the LibreSoft Power ISA decoder is implemented. So using a recursive function, yes, really, a recursive function which picks up different CSV files. So you have a major CSV file for the top level, and the data structure contains subdecoders for the minor 31, minor 19, etc., etc. To consider doing this in Verilog or VHDL would be frankly flat out insane. It's possible with Chisel 3, but again, Chisel 3 is not readable code by the majority of software engineers. You'd have to train them in the programming language first, and then train them in the HDL. So we can do even we can have extreme object-oriented abstraction to create dynamic partition signals that have the same operator overloaded add, subtract, greater than operators. I don't know if you're familiar, but in Python you can create an underscore add underscore function with your class, and then in your Python code you can do your object plus object 1 plus object 2, and simply by doing that it will call, so x plus y will call x dot underscore add underscore brackets y. And consequently, this very obvious level of abstraction we've used to create dynamic partition SIMD signals, which can the HDL will open up, depending on a signal, into partition. So you start off with 164-bit, but it opens up in partition gates and divides it down into 2 times 32, or 4 times 16, or 8 by 8-bit adds at runtime. And yet the code itself looks like a straightforward add. To consider doing that in VHDL or Verilog, I mean, it would be, you'd need 10 engineers to do the same job. So we're trained as software engineers. The entire project is run along standard Libre software project management, public bug tracker, public mailing lists, public IRC, public Git repository, and a charter. Did you notice the emphasis on the word public there? So it's all inspectable. Anybody can help. Anybody can join in. All our customers can look at it and see that we've got nothing to hide. And also, universities can join in and help with it. They can anything, the EU can come along and inspect auditors from our funding body can inspect it as well. Now, none of our engineers are hardware trained. They're all software engineers who learned HDL. And the other way around makes life really much harder when developing things. And very, very interestingly, IBM also for the power processors, Power 9, Power 10, they have required their engineers to be software trained in C and C++ as a primary requirement. They then train them to do HDL. The thing, and one of the reasons for that is because the tools that IBM use are written in C and C++. So, like Microwatt, we develop unit tests. We use Git revision control and the bug tracker. We've still got to do is to set up continuous integration. We've been meaning to do that for a long time, but it requires a machine that has quite huge resources. Unlike Michael, though, we have a wiki for all of our documentation, and this wiki is itself backed by a Git repository with full revision control. I cannot emphasize enough how critically important software engineering techniques are for large project management, and this is a large project. You need unit tests, you need unit tests, you need unit tests. And we went down as far as the module level. I am shocked at industry standard practices do not, I think most open source hardware projects do not use unit tests. They develop the whole thing and then do a high level integration test. What we did, if we wanted a module, we wrote a unit test for it. Then the code that used that module, we wrote a unit test for that. And then up and up and up and up. And finally, over this thing. So as a result, we've got literally thousands of unit tests. And this is just a standard practice for Python projects because it's a dynamic language. But regardless of what language you use, for goodness sake, you need unit tests, because otherwise you make one change at the low level, everything breaks. How do you find it? Yeah. So the other aspect is the auditability and transparency. We're funded by NLR's Privacy Enhanced Trust program. It turns out that this matches very well with the business objectives of the company Red Semiconductors that we're setting up, which is to provide customers with the ability to inspect down to gate level, to be able to inspect the GDS2 files. Now, strictly speaking, that would require for ASICs that have gone to NDA Foundry, the customer would also need to also sign the same NDA Foundry, Foundry NDA. Everything else for us will be publicly available. But to even consider this, it's impossible for Intel, ARM, Qualcomm, NVIDIA to do this. There's no way they're going to allow their customers to look at their HDL. But even if they agreed to do so, they still couldn't let the customers in because they've licensed HDL blocks from third parties. And they will be literally hit by a wall of lawyers, 1,000 lawyers, if they tried it. So, it's just not possible. For us, we deliberately went with Sorbonne University LIP6.France, Coriolis 2 tool, which is an entirely Libre licensed VLSI toolchain. You may have heard of how OpenRoad is zero config from HDL to GDS2. So is Coriolis 2, and it has existed since around 1993, developed by a French company, and then was assigned to LIP6.fr, who helped develop it. So it's actually quite a mature toolchain. We also have a cell library from Chips for Makers, which is called FlexLib. Again, it's written in Python, and it can auto-generate if you pass it the PDK, and it will generate the actual cell libraries. So it has boots on the ground. It has both a symbolic and real versions. Now, the symbolic version is public and published, no NDAs, and it uses free PDKs. Academic design kit, which means that we can create the thing. Now, the real version is NDA'd with the Foundry for 180 nanometer. Now, the critically important thing about this is that the LibreSoc team can work side by side with LIP6 without signing a Foundry NDA, and this is extremely important for academics to be able to actually publish the work that they're doing. And at the moment they're preventing the prohibited from doing so because they're signing foundry NDAs. Uh, you know, so this is deeply significant. Now, also available from Lib6 is something called NSX-Lib, which has been silicon proven in 180 nanometer and 360 nanometer. Right, so you could use that standard cell library as well, and they also have I/O pads available. So that's what they've been working with so far. Now that is a completely NDA-free, silicon-proven 180 nanometer cell library. Right, that means you can develop an entire ASIC and send the GDS2 files to any 180 nanometer lab. It's very similar to MOSIS, except MOSIS rules are very crude and blocky, and about double the size to be able to cope with things. But the Coriolis 2 Alliance NSX-Lib is much smaller. So, what was our development process? Well, we started with Namidia and HDL in Python. This then gets converted automatically to Verilog using Yosis, so we can then pass that to verification tools, even proprietary verification tools. You can extract and run it there. We developed several thousand unit tests at every level, starting at the HDL modules, going up for the integration of the modules at the next level up in the HDL. Then we ran FPGA unit tests. We had JTAG capable unit tests. We then extracted the HDL. When compiling the ASIC, it can be extracted similar to SPICE model. Well, actually, can now do SPICE models, but when you do the place and route, you can extract the laid out the actual routed netlist back out as a subset of VHDL. We then ran that through simulation and checked that as well. But as a last bullet point, I'm skipping ahead, sorry. We tried simulating the entire laid out ASIC as HDL. It required way too many resources. It would have needed 150 extremely powerful computers to compile it in a reasonable amount of time. So instead we did smaller ASICs, only 8,000 gates. But we did 8,000 gates with the PLL. We did 8,000 gates simulation with the SRAM, which completed in a reasonable amount of time. So Jean-Paul Chaput improved Coriolis 2 to cope with automated layout of 130 cells. We handed him the HDL. He automatically created a GDS2 file, which is now reproducible, no manual intervention. But he had to do a significant amount of improvement to Coriolis 2 to cope, because the last largest cells it was able to do was about 10,000 cells. We're over 10 times that amount. Consequently, he had to add buffers, because we're driving in some cases as many as 80, particularly for the SRAM. We're driving 80 things, so you have to have a cascade of buffers. He also, because of the much larger size, he had to add antenna in, and those antenna diodes are inserted automatically. All right, it's not. None of it has to be done. There's no post modifications, scripts, etc., etc. Um, Chips for Maker's Flex Cell Library, the standard cell library, also needed development, and that included staff also very kindly developed a custom 4K SRAM block for us, which unfortunately is under NDA, so we can't show you that because it needed information which was at the low level. The foundry 180 nanometer foundry level. Professor Galialco developed a voltage controlled PLL for us, a voltage controlled oscillator. It's capable of running, and he did spice simulations, and it was capable of running between 150 and 900 megahertz, which is fantastic. And so when divided by 2, that means that in theory we could run at 450 megahertz. Our target was 300. But he also included a digital divider, so it can be that 300 can be divided down to 150, 75, 37.5. So we'll be able to test a range of frequencies of the chip when we get it back from the foundry. Marie Reneuve Laura very kindly was responsible for the HITAS static timing analysis tool for developing it and then running it for us, and that we passed 100% on the timing analysis. As I said earlier, we tried simulating the laid out ASIC, but it was way too many resources. So we did the smaller test chips, taking components that were used, and those passed. And one of them, Professor Galiaco, actually did a SPICE simulation, full SPICE simulation to several picoseconds, several thousand picoseconds. Of the PLL and one of the small test ASICs, and that worked fine as well. So this was the ASIC diagram that was sent to TSMC. You can see here in this top corner there's the actual quad flat package that was used. TSMC need this diagram containing the pinouts for the boundary scan here, plus an identification tag in this corner, which they will be able to send to the factory to get the orientation right. But they wanted the pin diagrams, etc., to make sure the thing, and they also wanted it with the orientation tag in the diagram. And this contains all of the information that they need to actually create the test chips for us. So that should be back from IMEC within a few months, and we will be able to begin the testing process. So that's it. Thank you so much for your time and attention. Any questions?